So a couple of weeks ago we started talking about addition reactions. Just to refresh your memory, I'd like to give you an example. And the example that I used in lecture was that of 3-methyl-1-butene. And in 3-methyl-1-butene, among other things, we added the elements of HBr across a double bond. Mechanistically, we saw that the pi electrons served as the most reactive nucleophile. The partially positively charged hydrogen atom served as our best electrophile, and that the partially negatively charged bromine served as our leaving group. And after rearrangement, we found that our major product was 2-bromo, 2-methyl-butane. This, of course, was an example of an addition reaction. The addition reaction was driven forward by low enthalpy. Again, to refresh your memories, what we found is that we broke a weak pi bond and we made 2 strong sigma bonds. Now we're going to study the reverse reaction. That is, taking an alkyl halide and removing the elements of HBr or HX, where X is a halide, could be a protonated alcohol, simply any group of atoms that's capable of an independent existence. That is, any group of atoms that can serve as a good leaving group. And we're going to convert one molecule into 2 molecules. This is called elimination. And elimination is not going to be favored by low enthalpy, but rather by high entropy. So there is a fundamental difference between the driving force of a forward reaction and, of course, its reverse reaction, which I think only makes good chemical common sense. So let's say that we have the following alkyl halide. In elimination, we are going to remove the elements of HX. In this case, we're going to lose the elements of HBr, and we will produce a mixture of alkenes. One will be the major alkene, one will be the minor alkene. Regardless of the mechanism. And we're going to find that just like in substitution, we can have a mechanism that is concerted, that is a mechanism that essentially occurs in one step. We're going to call this concerted elimination mechanism an E2 elimination. Again, this is a kinetics term. The old antiquated biochemical term for this is called beta elimination. And just like with substitution, we're going to find that we can have a stepwise mechanism we will call this the E1 pathway. E2, like its SN2 counterpart, is by far and away the most commonly encountered elimination mechanism found in nature. And the vast majority of our effort in this unit will surround the E2 elimination. What I would like to do in a very general sense is to contrast the steps, the mechanism, and the potential energy diagram of the E2 elimination and the E1 elimination. In subsequent OSCAsts, I'm going to break these down even in more fundamental ways so that we come away with an excellent grasp on the stereoselectivity, stereospecificity, and other aspects of these reactions so that we truly have a firm mastery on these topics. So let's take a look at the most common of the two, which is the E2 elimination. And in the E2 elimination, I'm going to start with an alkyl halide. That shows some chirality. And so when we take a closer look at this structure with regard to the stereochemistry, this is our starting material. Now, as a review, why don't we take some time and let's name this compound in terms of its stereochemistry. So let's start with this chiral carbon. Bromine, of course, is my top priority. Hydrogen is my fourth priority. The substituted carbon is my second priority, leaving the methyl group as my third priority. As I go from 1 to 2 to 3, I move in a clockwise direction, but I really need to flip my answer because the low priority is coming out of the plane of the screen towards me. So this is going to be 2s. We must label the carbons in this way because the bromine needs to have the lowest number possible. So I'm going to number these with Roman numerals. So we have 2s. And now let's go to carbon number 3. With carbon number 3, we find, and again, you got to be careful here because this looks like it has chirality, but it really doesn't because I have two methyl groups. So going back and adjusting this, this will be S 2 bromo butane. Now, in a very generalized sense, this compound can be drawn in terms of the carbon-carbon double bond that's going to form, the hydrogen that's going to be removed, and the bromine that's going to be removed. And in this mechanism, rather than having a nucleophile, we're going to have a base. The base is usually bulky so that it can't attack the electrophilic carbon, but rather is positioned to remove this accessible beta hydrogen. In an alkyl halide, the carbon that is most electrophilic is the alpha carbon, and an adjacent carbon is the beta carbon. We're going to form a double bond between the alpha carbon and the beta carbon. And of course, our leaving group will accept the electrons and go away. This all occurs in one step in beta elimination to yield a carbon-carbon double bond. The most important element of this particular mechanism is the fact that the hydrogen, both of the carbons, and the bromine atom all have to lie in one plane, and that the hydrogen and the bromine, in order to minimize steric hindrance, have to be anti one to another. So there's a dihedral angle here that must be greater than 175 degrees, but in actuality is a little bit less than 180 degrees. This arrangement is called anti-periplanar. And I must have an anti-periplanar arrangement of the two elements that I'm going to remove in order to produce an alkene. Because of this arrangement, I have a stereo-specific reaction. Normally, I will not be able to produce both the E-alkene, or the trans-like alkene, and the cis-alkene. Now, in this particular model, I have not shown the bromine and the hydrogen that I can remove anti one to another. So again, we're going to have to build a model or turn this into a projection such that it is clear on the relative orientation of the hydrogen and the bromine one to another. Also notice I'm also considering a product from the most substituted alkene only. I could also remove a beta hydrogen from the exterior carbon as well. Again, as we delve into more detail with the E2 reaction mechanism, this will become more obvious, but I'm not going to get into that kind of detail on this particular Ozcast. So first thing is, let's get these carbons such that the bromine and the hydrogen are anti one to another. One thing that we could do is simply draw a Newman projection. And in the Newman projection, let's look down the C2-C3 bond axis. I'm going to have a methyl group oriented at the top. I will have a hydrogen rotated to the right and a bromine rotated to the left. And in fact, I'm going to take the time to highlight this bromine because this is one of my groups that's going to leave. And I'm going to circle that. Now, on the back carbon, I'm going to render this in red as I look down this bond axis. I'm going to have the hydrogen to the right. The methyl group will be coming down, which leaves the methyl group, which leaves another methyl group to the left. And again, the hydrogen that is going to be removed, I'm going to render in white and also circle. So really what I need to do is to rotate this back bond by 240 degrees. And when I rotate this by 240 degrees, the most stable Newman projection will be this. So I'm going to keep the front carbon the same. Now this hydrogen must be over here. Notice that is anti to the bromine. And of course, I'll have a methyl group. And another methyl group. That means these guys are going to leave, the bromine and the hydrogen. I'll make a carbon-carbon double bond. And I really can't explore the stereospecificity of this reaction because this doesn't exist as cis and trans geometrical isomers, because both of these methyl groups are equivalent. So if I were to draw what I would perceive as the cis isomer, these two would superimpose and they'd be identical compounds. If I look at the potential energy diagram, I think we'll see some striking similarities to the SN2 reaction. So let's take a look at that. So if we graph enthalpy as a function of reaction progress, of course, notice that we'll have the energy of our reactant, which in this case is an alkyl halide, remember, this reaction is entropically favored, but not enthalpically favored. In other words, we are going to have an endothermic reaction because we're trading 2 sigma bonds for 1 pi bond. The payoff is entropically because we'll also produce a molecule of HBr. In the transition state, this leaving group is beginning to leave. The hydrogen is beginning to be broken as it makes a bond with the base. Of course, the base should be partially positively charged, and the bromine should be partially negatively charged. Also, by the Hammond postulate, notice that the transition state should resemble the energy of the products rather the energy of the reactants. That means that the carbon-bromine bond is going to be more broken than the pi bond is going to be formed. Of course, the pi bond is an intermediate as well. So in our transition state, you have the pi bond beginning to form, the carbon-bromine bond beginning to break, a base hydrogen bond beginning to make, a carbon-hydrogen bond beginning to break. And we only have one transition state, no intermediates. So our energy of activation points to the only step, which is the slow step. And again, I'll delve into this in more detail later. Now, as you might expect, there's going to be a stepwise counterpart to the E2 mechanism. So I'm going to start with the same substrate. First step of the mechanism, we have a leaving group that leaves. Of course, this will leave us with a carbocation intermediate. Get a carbocation rearrangement, just as we've discussed previously. This gives us the more stable carbocation intermediate. And in the last step, the base is going to abstract this proton to alleviate the positively charged carbocation intermediate, yielding the alkene. So again, we need to look at the potential energy diagram. So again, this will be similar to an SN1 reaction coordinate diagram. Again, we have enthalpy as a function of reaction coordinate. It's an endothermic reaction. Of course, our starting material our major product. In the first step, carbon Br is starting to break. The Br is partially negatively charged. Carbocation is partially positively charged. You've made this secondary carbocation in the first intermediate. You begin to see a rearrangement, a hydride shift, to give the tertiary carbocation. And the last transition state you're going to begin to abstract a hydrogen from a base and make the carbon-carbon double bond. And of course, in the product, you've already created this bond. Again, the delta H is greater than 0 in this case. The energy of activation is the formation of the least stable intermediate. At this point, y'all should feel pretty comfortable in drawing these potential energy diagrams. So this at least gets us into the conversation regarding elimination. What you can expect from me this weekend is one more that's completely detailed on E1, and yet another that's completely detailed on E2, and a third Ozcast in which we look at the competition between E1, E2, SN1, and SN2.